Our title today are Trends in Atomic Radii. So what we're referring to here is the distance between this clearly not to scale model of an atom. The distance between the nucleus and the valence shell of electrons, right? The radius of an atom. So what we've got to keep in mind here, and what we know, is as we move across a period, we are getting ever-increasing numbers of protons and electrons. So as we move to the right, we add, or what we see happening with elements is that the number of protons is increasing by 1, and the number of electrons is increasing by 1. So it would be fair to think that as we move across the periodic table, we should find an increase in the size of the radius of an atom. But what we find is counter to that. That as we move across a period in the periodic table, we actually find that the radius of the atom of those elements continues to decrease, so that once we get all the way over to group 8, for that period, we have the smallest sized atom in terms of radius. So why is that the case? Let's explain that trend. So, atomic radii in general usually decrease as we go from left to right across a period on the periodic table or row. So what we're looking at here, you guys, we're going to look at patterns. Patterns in radii, repeating patterns that we see on the periodic table. Periodic meaning repeating patterns. And we call those things trends. So as we move from left to right, the radii, the radius of an atom decreases, which again is very counterintuitive. So why is that? Well, because of something called effective nuclear charge. So effective nuclear charge increases across a period. And as the effective nuclear charge increases, it attracts the electrons to the nucleus more strongly, meaning that it will tighten up the radius of the atom. Everything moves closer in towards the nucleus of the atom. We've got this positively charged nucleus, and we have these negatively charged quantum levels of electrons. And it is the unlike charge, the electrostatic attraction, meaning that the positives are attracting the negatives that hold these electrons in orbit around the nucleus. The greater the pull here, the closer these things are going to move in. So the greater the force, the closer these things are going to be, the greater the attractive force, the greater the Coulombic interaction. Okay, so what happens? What is this effective nuclear charge that I speak of? And I will explain it a little bit more in class, for sure. But as we move across a period, what we know is that all of these electrons are being added to the same quantum shell of electrons. So we're not adding electrons to any quantum levels further out. We are adding them at the same distance. And as we are adding them at the same distance, what happens is we are getting an ever-increasing number of protons in the nucleus, which is increasing the nuclear charge. And because those protons are acting at the same distance, because the electrons are all being added at the same quantum level, we say that as we go across, we are getting greater effective nuclear charge. But more about this in class tomorrow. Okay, so what about as we go down? What do you think happens to the nucleus, the radius of an atom, as we go down a group? And this one is much easier to visualize what would happen. So as we go down a group, not surprisingly, the radius increases. But it's not just simply because we are adding more protons and electrons to the atom. That's not the case. I mean, it's true, but that's not the reason, you guys. As we go down through a group, we are having electrons existing in quantum levels further and further from the nucleus. So what we know is that the valence shell is in quantum level 1. The valence electrons are in quantum level 2. Valence electrons are in quantum level 3, quantum level 4, 5, 6, 7. So as we go down a group, the valence electrons are existing in quantum levels ever further from the nucleus. Let's talk about ions. Positively charged ions have a smaller radius than the neutral atom because there is less electron-electron repulsion. So let's just do a quick review of an positively charged ion, a cation. So let's look at potassium. Potassium atom has 19 protons and 19 electrons. Keeping in mind that these 19 electrons are all negatively charged, correct? So they repel, a negative and a negative repel. So they're always at this, there's always this game going on, this push and pull going on. The pull of the nucleus, but the push of the electrons against each other. If we can get rid of one of those electrons, we've still got 19 protons here. But because it's positively charged, positively one-charged ion, how many electrons do we have? We've got 18, because this thing has given up its single valence electron. We've got less electrons. So now we have less of this electron-electron repulsion, less of this negative charge repulsion, so everything can just tighten up. So cations have a smaller radius than the neutral atom. Let's think about this potassium atom, because this potassium ion, this isn't always the case, but the majority of the time it is the case that when you form a cation, okay, so we've got potassium atom with 19 electrons, potassium ion with 18 electrons. Where is that one valence electron for the potassium atom? The valence electron for the potassium atom is in quantum level 4. Once we have gotten rid of this valence electron, where is the valence electrons now for the potassium ion? Well, the valence electrons for the potassium ion are in quantum level 3. So for this, the valence, N equals 4. The quantum level is 4. For the potassium ion, it's given up its valence electrons, and now it's a valence electron. Where is its valence now? Its valence is in quantum level 3, which is significantly closer to the nucleus. So not only less electron-electron repulsion, but most of the time when you form a cation, you are losing all of the valence electrons, and now the valence actually is one quantum level closer to the nucleus. So what do you think about anions? Anions have a larger radius than the neutral atom because there is more electron-electron repulsion. So if we look at something like bromine as opposed to bromide. Bromine has an atomic number of 35. Protons, 35 electrons. The anion, 35 protons. 36 electrons. Okay, this is going to have a larger radius. Why is it going to have a larger radius compared to that? It's going to have a larger radius because there are more electrons now, and not just because there's more electrons. Keeping in mind, you guys, they're all at the same quantum level. But because there's more electrons, there's more electron-electron repulsion, and that's going to swell those things up. Okay.